Okay. Then, ladies and gentlemen, thank you very much for attending our today's webinar. My name is George Kodros. I'm the Managing Director of Labthink GmbH, the German branch, the European branch of Labthink. We organize this webinar expecting that it will touch an area of testing that usually we don't focus much, but after the introduction in the market of our film shrinkage tester, the new film shrinkage tester, we believe that there should be an interest, and therefore we offer you this training webinar. The subject is determination of shrinkage stress and measurement of contraction stress. We are going to have an introductive presentation from the International Sales Director of Labthink, Mr. Martin Bryant. And then we're going to offer you a live demonstration directly from our laboratory, from our technical director, Mr. Alex Plop, who is going to show you the tester, who is going to share with you the software, and also show you how we use, prepare, and test the samples. So I don't want to take more of your time. I wish you a lot of enjoy. And at the end of the meeting or during the meeting, you can post in the chat department your questions, and our technical department will answer afterwards all together after the presentation is over. Enjoy.
Thank you, George. Yes, as George says, my name is Martin Bryant. I'm the sales director for Labthink International, and I've been with the company around 10 years. And today we're going to talk about shrinkage force measurement ratio and the measurement of contraction force. So we have developed a very interesting instrument that fully automates this process with a high degree of accuracy, and it's a multi-function instrument which gives you several measurements in one piece of equipment. So the presentation will be divided into 4 parts. The first part, where we're going to be looking at the application of the test itself and then comparing 2 different test methods. I'll introduce you to the Labthink C631H film shrinkage tester. There'll be a short video there, and then we'll end the slideshow and proceed to a demonstration by Alex Plop, who, as George says, is our technical director based in Frankfurt, Germany. So first up, let's take a look at the applications of the shrinkage test. So some of you will be already involved with the manufacture of shrink film materials. Some of you might be looking at this as a new business opportunity or just through curiosity. So there are a couple of different ways of measuring some of these characteristics. One is an unrestrained linear test, or some people refer to this as a film-free shrinkage test. And then the Labthink instrument that we're going to talk about today and the method that it uses, we call that thermal shrinkage. And it's applicable to a range of different materials, such as polyethylene, ethylene, copolymers, and mixtures. And the importance of the test with regard to the characterization of the film shrinkage is that if we take an example where somebody's making perhaps sleeves for thin wall bottles, such as water bottles, those containers are quite fragile, and it's very important that the shrink sleeves fit the bottles tightly, but not so tight as to deform them or damage them. And so it's vital to make sure that the materials that are designed for the purpose of manufacturing the sleeves have the appropriate shrinkage characteristics. Likewise, at the next stage of the process, where the bottles are packed into trays, and then again shrink wrap, typically with some kind of polyethylene wrap. It's important then that the overwrap is not so strong as to crush the bottles, but likewise it cannot be so loose as to permit them to move around very much. So in some cases where trays of bottles are retailed by supermarkets or kind of large outlets, like commercial outlets that supply restaurants and such like, people often pick the trays up by one end of the shrink wrap in a place which is called the bullseye. And what happens is if it's not been correctly wrapped, then the bottles fall out and they fall on the floor. And it's a very important consideration financially for some people. Some of those retailers impose a penalty for every tray that is damaged, even when it's damaged by the customers. And so it does tend to damage the reputation of the supplier. And it also imposes some kind of financial penalty. So you can see why it's very important that the film is developed and applied correctly. So in the manufacturing process, some of you know, the films, the polymer change can be orientated in such a way as to deliver the necessary stress characteristics, and that stress is locked in to the material. And when the film is heated, the stress is released. So at that point, the material tends to try and return to its original molecular structure, and in doing that, it shrinks. And the magnitude of the shrinkage will vary with the temperature of the film and the time with which it's exposed to the temperature. And so using a process of iteration, you can develop materials which will provide the optimum characteristics of shrinkage force and shrinkage ratio. And then the contraction force, which is the third parameter which we measure, is concerned with what happens when the materials emerge from the shrink tunnel and begin to cool down. So there's a second phase to the process. You have the initial shrinkage at the high temperature or higher temperature, and then there's another phase of shrinkage which occurs as the material cools down. So this method, which the Labthink instrument employs, is capable of measuring the shrinkage force while the material is subject to heat. And it's also capable of measuring the contraction force as the material cools down. And with another dimension, it can also measure the shrinkage ratio. So the two different test methods with which shrink film manufacturers may be concerned is manual testing, which is ASTM D2732 or ISO 11501, and the automatic test, which is where we're focusing today, is the ISO 14616. So those are the two standards with which we're trying to facilitate compliance. So comparing these two methods, D2732 will only give you the shrinkage ratio. So of some use, but not ultimately use if you want to find out at what temperature your material should be processed to provide the ultimate shrinkage force and contracting force to grip or apply to the product. So we use ISO 14616. And then there is a difference in the heating method between the two standards. D2732 uses silicon oil in a heated bath, and the ISO 14616 uses air as the heating medium. So the calculation of the results also differs with 2732. It's, as I said, it's a manual method. And so the calculation of the result is manually performed by the operator. 14616, or 14616, I should say, is a fully automatic calculation. And so there's less room for human error, and the results are contained within the instrument, and so you can recall them later on and create test reports and so on and so forth. There's also a difference in the parameters specified within the two standards. So D2732 says that you must maintain the accuracy of the temperature to within plus or minus 1 degree Celsius, 14616 plus or minus 2 degrees. And then because there are no force or displacement measurements with 2732, there is no data there. With regard to 14616, it's plus or minus 2% of full scale or 0.4 newtons, and a displacement accuracy of plus or minus 1 millimeter. And so if you care to remember those, when we discuss the specification of the C631H, we'll refer back to these and compare them. So here we are looking at the two different methods. On the left, we have the silicon oil bath. So you can see it's a fairly simple to understand operation. You have a bath of silicon oil. It's heated up. The test specimen is measured, placed within a restraining cage, and then it's dipped or placed into the heated oil for 10 seconds, removed, and measurements taken manually as to how much it has changed in dimensions. And from that, you can calculate the shrinkage ratio. With the other method, we have some different sensors involved, and it's a more mechanical method. So if you concentrate on the drawing rather than the picture or photograph of the instrument, you can see that there are two specimens there. Between the specimens in the diagram is a thermocouple which controls the temperature of the environment around the specimens. In the picture, one of the specimens is connected to a cable displacement sensor. So as it heats and shrinks, the cable moves, and you calculate the displacement using the cable transducer. The other one is connected to a small load cell, and this was the way that an earlier iteration of the C631H worked. That was the available technology to us at the time, and we developed an instrument based upon that. The C631H differs from this in that we have introduced a more sensitive technology to improve the accuracy and efficiency of the instrument. Finally, the final comparison, we can say that because we only use air with C631H, it's more environmentally friendly. You need to change the silicon oil. If it's overheated, it can be what we call burnt. It's wasteful, and you have the problem of disposal, which is all fine, but we're talking about very small quantities here. In my opinion, the biggest difference between these two methods, apart from the range of results which you can achieve with the more sophisticated instrument and the technology used, is that having the silicon oil in the laboratory, to me, presents a health and safety issue, and it also is a housekeeping problem. Nobody wants to be around hot silicon oil and the risk of spilling it, getting burnt by it, trying to clean it up, and then dispose of it. It's very difficult to clean up, and its disposal presents a problem. So to me, the biggest issue with this test is health and safety and housekeeping. The environmental consideration is really secondary. So let's introduce the instrument. So here's a kind of timeline of development. So first of all, we have the silicon bath type instrument, which we still make. Some people still desire to use this method. It's rudimentary, and as a result, it's inexpensive. We try to make it as safe and as easy to use as possible, but there are limits to how much you can do with it. As the popularity of shrink film wrapped or encased products has taken off, Labthink developed two other instruments, the film shrinkage tester 01 and 02. And these used sort of micro load cells, and also they had linear LVDT transducers in them to measure the shrinkage or displacement of the film as it shrank. Those instruments were good, but they weren't as accurate or precise as we wanted them to be. And so we introduced the next one, which is the Thermatech 2720. This had the cable displacement sensor inside. And that was an improvement for certain, but there's still a degree of inaccuracy or imprecision due to the friction of the system, the internal friction of the cable transducer. And so we developed this one, C631H. And this consists of a heating chamber, two sample grips, the thermocouple, which monitors the temperature of the heated chamber, some indicator lights on the front which show you at which stage of the process the machine is operating at any time. And there is also some components which are not illustrated on the slide here. The machine has its own internal computer for processing the data and for giving the machine its control instructions. And those control instructions and the visibility of the data are handled by an external computer monitor, and else, flat screen monitor, a keyboard and a mouse, which is also included as part of the system. Inside the instrument, as I say, you've got two samples there. You can see on the left, there's one for shrinkage ratio detection, and on the right, the one for shrinkage force detection. Here is the big difference, though, that in this iteration of the product, the measurement of the shrinkage ratio is done via a laser displacement sensor. So the friction that we encountered with the LVDT transducers and the cable transducer is eliminated. So this is a frictionless system, and so it provides a much more accurate and precise measurement of the change in the dimensions of the samples. One component that you cannot see in the diagram is there is a small target, which is a T-piece or T-shaped piece of material, which is attached to the bottom of the shrinkage ratio specimen, and that constitutes the target to which the laser, excuse me, to which the laser is aimed during the process. Then on the other side, the force shrinkage specimen, it's clamped up. One you can see at the top there, it's affixed to a fixed rail, so that end is not going to move around. And on the bottom, it's clamped up to a high accuracy load cell. So in as far as it's possible for us to do this, we've designed something which is intended to simulate the behavior of the film within the shrinkage tunnel. So there's we see that the advantages that we have the laser displacement sensor. This has been put into with the intention of reducing friction, and so the transition from the first instrument to the current iteration is that the friction effect with the LVDT was approximately 0.08 newtons. That was improved with the cable displacement transducer, which gave us a friction factor of 0.04 newtons. And now with the laser, as I say, it's virtually friction-free, 0.002 newtons. And that small difference is simply due to the mass of the small T-shaped target, which is fixed to the bottom of the ratio measurement specimen. And so with this system, we can get an accuracy of plus or minus 0.1 millimeters. So the force measurement is achieved with high precision miniature load cells. Like all the components that we use in all of our products, we only use those which are supplied by internationally recognized manufacturers. This gives us an accuracy higher than 0.5% of full scale and very good repeatability of the test results. One of the instruments, the FST series, those also had a pneumatic driving system which delivered the specimens to the oven or heated chamber. That resulted in some vibrations, which we've eliminated. Those had an effect of about 0.15 newtons deviation on the force measurement. That's gone now, and so we believe that we've arrived at the most precise and accurate instrument that we could develop. And using the air medium, we have an accuracy of plus or minus 0.5 degrees centigrade with a variation of plus or minus 0.2. If you remember a couple of slides ago, the specimen parameters recommended were plus or minus 2 degrees Celsius. And so this is well within the desired ranges as specified in the standard. And as the instrument is computerized, we call it intelligent control. It was fully automatic. The software is embedded inside, so you get professional looking reports and the capability of storing and handling and presenting the data. So although it's difficult to see, and I'm sure my colleague Alex will show us one of the reports, or you'll be able to see the software on the screen to see what you have. Basically, when preparing for the test, you have the option of inputting a number of different characters or fields of information, which can include things like the lot number, the batch number, the thickness, test conditions, what the name of the material is, and so on and so forth. And at the end of or conclusion of the test, this data can be presented in a report along with a data curve of the shrinkage ratio and force measurements. And so it's a useful addition when you're preparing like certificates of analysis for customers. You can back that measure that data up with reports like this. They can also be very useful for maintaining historical records of the development process and how certain features of the film were determined. It's very easy to use. It's a great instrument for doing R&D tests. There's no messy cleanup of the specimens after each iteration, so you can run through several scenarios of temperature and time of test very quickly and very easy. So it's very efficient. Not very much labor cost involved, really. It's just the preparation of the specimens and starting the machine and monitoring the results. And as I mentioned, it's environmentally friendly, but more importantly, it's much less of a safety hazard than the oil bath method. So we have here a short video. I'm going to turn the sound down on this just to save some bandwidth. This is a very short promotional video, and my colleague Alex will get into more technical detail. And you can see there the attachment to the computer monitor. So that just gives you an overview of what it actually looks like. You can see the clamping pieces there. You can see the thermocouple, you can see the status indicator lights, and so on and so forth. So that, you know, that gives you an idea of what it would look like in your laboratory. So that kind of brings us to the end of the slideshow part of today's webinar. I hope I've been able to illustrate that we follow a rigorous kind of R&D process. We have almost 100 patents now. About 50% of those are related to permeation measurement, where it's our intention to be the leading company in that particular technique. The other 50% are related to a wide range of mechanical measurement instruments, of which the C631H is one of them. And if we combine those mechanical instruments with the permeation measurements, it means we have pretty much the most complete line of permeation devices and other measurement devices, and so that customers can meet most of their demands by working with one company. Over the past probably 18 months or so, 2 years maybe, the company has really developed exponentially. We now have offices all over the world. The USA company is headquartered in Boston, serves South and North American customers. George, who made the introduction as the managing director of Labthink GmbH, is located in our offices in Frankfurt, Germany, serving all of our European customers. And in the Middle East, we have an office in Dubai, which looks after Middle East and African countries. And lastly, the most recent addition is an office in Kuala Lumpur, Malaysia, which looks after the Far Eastern Asian countries. So we truly are devoted now to aggressively expanding our company and making sure that we're capable of satisfying most interests for packaging materials and thin materials testing. So that's a kind of summary at the end, just to wrap up things. I'm going to now just say thank you for your attention while I ran through this, and now I'm going to hand this over to Alex Plopp, our technical director based in Frankfurt, Germany, who is going to run through a more in-depth video presentation of the instrument. So over to you, Alex.
Hello, everyone. Thank you for joining. I'm going to also open my camera. I hope you can see our tester. Maybe you can. I think you can see it, right?
Yes, Alex. Yep.
Okay, so if you can see us, welcome and thank you again, everyone. We're just gonna quickly present to you the tester. As Martin was saying, to set up the tester is quite easy. You don't need a lot of resources, so you just need a stable workbench. You need to have access to electricity, and one important aspect of this tester is that the software is embedded, so you don't need to have some expensive PC next to it. You just need to connect to the main tester, to the tester itself, a monitor, the keyboard and a mouse, and then you are set to work with the tester. So it's quite easy and straightforward to install. Here inside, where we have the incubator or the testing area, we have two sensors. So we have the load cell. My colleague is helping me to get closer to it. So we check the shrinkage force on the right hand side, and then the left we check the shrinkage ratio, and we use an infrared sensor for this. Here the incubator door will fall down as needed when we start a test, and this is what is happening, because we get a lot of questions what is happening in the middle. This is the sensor that monitors the actual temperature inside to know exactly when the desired temperature is reached. Now we're going to show you quickly, because the tester comes together with all the accessories needed to prepare these samples. We're going to try to show you quickly the tools needed to prepare. So our film will be covered with the plate. We'll use a cutter to make this stripes of film, and then finally we will use this supports to prepare our sample. I hope you can see my hand. So it's quite easy and straightforward to prepare the samples. And like we were telling you, these are all included in the initial package. Now we would like to switch to the software side. So once we have our samples prepared and installed into the tester, we simply operate the test and the tester with a mouse from the monitor. Obviously, first we will go to parameters, but first let me show you and present to you the main screen. This is the main and the user interface where we will see the graphs to the left-hand side. To the right, we will see the test status. So in this window, at all times, the operators and the ones next to the tester will know what is happening with the tester on the screen. And to the bottom, we will have to the left the test data, so the data that we desire to collect. And from the bottom right, we will have the test control. So these are the buttons that help us to control the tester. Going to the parameters, in the first part of the screen, we have all the information that we as operator can add. So the test name, specimen material ID, operator, and all this necessary information for the test reports. And at the end, to the last selections, we have the most important ones, which are noted with a small star, special and important information like the specimen thickness, the test temperature that we desire, and you can see that we are the tester has quite generous range, so we can test from 25 degrees Celsius to 210 degrees Celsius. We can set an end temperature, and we have two different test modes. So we have the specimen out by time or by force. So this will allow me to personalize the test to end it when a specific amount of time passed, or when my film has seized a specific force. Then we also, in this case, we can set the time, and we have also two detection modes. So the test, the detection could start when it's entering the heating chamber, so when the window of the chamber falls down, or when reaching the setting temperature. So if I set a specific 100 degrees Celsius, this means the test will start only when this temperature is reached. After I have my selection, I just simply submit, and then I am ready to go. From the bottom right, I can just control the tester. For example, I can just start the temperature control for my chamber, and then when I'm ready, I can just start a test. Now I see on my screen that the temperature is being controlled, so it's going to be some minutes until it reaches the desired and the set 100 degrees Celsius, of course. But we can wait for this, and I can tell you what happens when the test actually finishes. When the test actually finishes, the system itself, the tester itself, will generate a report that I can see here. So we can at all times come back and review all the tests that have been done to our tester. So an advantage for the operator is that they don't have to worry about saving an actual report. It's going to be automatically saved here, and then from this I can select it from this list. I can select it and I can actually open it so I can see it. Here, it's also, again, an area where I can actually personalize my reports. So I can, again, add information that maybe I have missed when I submitted my parameters. And I can personalize the report, what courses and what graphs I should have. If I'm happy with the selection that I've made, I can just hit preview. And then you can see here how my report has been generated. So I have the first graph for the force, and then I can go next where I can have the shrinkage ratio. So I can see where the test started. Here's where the shrinkage of the film was actually happening during the test. And obviously here I have a plateau. So this is where the sample got stabilized. These reports can be saved on a USB stick, so you can use them later. And you can also delete them, obviously, but the most important part is that you can save them and use them in your everyday work. The software has a lot of features. To name another one other than the report section, it's that it has a user management. So, for example, for the lab managers that would like to create and add some usernames to each operator, you have the possibility of doing so from here. And another important aspect, it's the parameter program. So, for example, if you have your own customers that you already work with and you know that they have desired parameters to work with, in order to save time and human error, obviously, you can create a list like we have here for in our demo tester, just the two of them, where you have a preset of already the desired temperatures and modes, like I was showing to you in the parameter section. So they are already preset, and then the operator does not need to input them each time. Then they will just come to this list, select the desired list, the desired preset, and then you can set as default or load program. And then all the information that were set in that specific program will be automatically uploaded here, and I just simply need to submit. Also, another important thing, it's the operation log. So again, like the reports, everything, like the reports that are all of them saved, also the operation log, everything that is being done by all the operators on the tester is going to be saved here. So in case of some events that we would like to review after some time, we can refer always into this section. We also have a self-check, so we can always check if the sensors, the hardware, and in case that the tester is customized for a network connection, we can check. So now we are not linked, but you can see that the load cell works normal. The sensor for the IR sensor works normal. We have enough or sufficient hard disk space. And then obviously, because we're not connected right now, it says unchecked for the network, but this would be. If in case, I'm just going to show you once more the chamber to show you how, in case if a test will start, this is how the chamber will flow. So this ensures the tester to reach the desired temperature, but also to protect our operators so accidents will not happen. And from us for now, this is it. Thank you, everyone. If you have questions, please let us know.
Thank you very much, Alex. It was really instructive and informative. This is the presentation and the demonstration about the film shrink tester of Labthink. It's a brand new product. And now it's the time to go on with answers to your questions. Just a note before that. As you have seen, the session has been recorded, and the webinar video will be available for all of you to download it through from our website. Soon, all the participants are going to receive an email with the link to download the video. Now, to the questions. I have a question from Mr. Fasil. How many samples are tested in a single test? I could bet one, but Mr. Plop, please
Yes,
answer.
yes. Thank you for the question. So maybe I can open again the camera so we can show you one more. So for the test to make complete sense would be the same type, but again, will be one with the load cell. So it's going to be measured the force, and the other one with the infrared sensor is going to be measured the shrinkage ratio. So to make sense will be the same type, but it's going to be installed in two different sensors for two different data.
Okay, then
Thank you.
correct me for what I understood. For each type of sample, we need two stripes, which we simultaneously test, and we get for one sample type, one test each time. Is it okay?
This is correct. This is correct. Thank you.
Okay, thank you. I have also a question from Mr. Guidolin. Do you have feedback on experiments with films that include in the formulation some mineral fillers or compounds? Mr. Guidolin, right now, I think we cannot offer you an answer, but I have noted your question, and our technical department is soon going to contact you and provide you an answer. And thank you too. Mr. Fasil continues his initial question and says that FST02 allow 3 samples at a time. So what's the advantage in changing to C631? Martin, could you please elaborate with a reply?
Yes, George. So yes, you're correct, Faisal. The earlier models did have a capacity for more measurements, so you could measure 3 specimens for shrinkage force and 3 specimens for shrinkage ratio at the same time. But the accuracy of the test was not, in our opinion, satisfactory for certain types of materials. So some of the materials had very small forces and ratios to measure. And as I sort of hinted at during the presentation, the LVDT transducers that those instruments used had a steel rod inside a glass tube, and the friction of the movement of the rod inside the glass tube created a degree of friction, and that degree of friction, of course, influenced the results. So some users were experiencing problems in measuring materials which had very small shrinkage ratios, and then we had some customers with the load cell. I think the load cell on those instruments was 30 newtons, and that at the time was the best that we could put in there. With the C631H, the architecture of it, or the construction of it, and the way that it's been designed allows us to put in the maximum of 30 newtons, but typically the instrument would be equipped with 5 newtons or 10 newtons, and so the measurement sensitivity of the new instrument is much better. Admittedly, it sacrifices the capacity of the earlier models. So thank you for your question.
Yeah, and I think, Mr. Fasil, it is a well-stated answer. What I could add is that we have a new generation of tester, you might have a capacity lower than in testing capacity lower than the previous model, but you have a technology which is much more sophisticated, and you can have much better accuracy. So it is a new generation that we will strongly recommend. Now, Mr. Corey Lamb has a question for Alex Plop. So when we measure a sample 10 times, would you recommend averaging the results? Alex?
Sorry, yeah, I'm here. Thank you for the question. I just want to ask one before, the same exact sample or the same type?
Probably it's the same sample, because the question is, when we measure a sample 10 times, would you recommend averaging the results?
Well, normally no. We recommend always to prepare a new sample for each test. Sample cannot be retested. So, for example, if it's going to shrink, then obviously even a little bit, then obviously on the second time it's not going to give. It's going to give an accurate result, but it's not going to be in accordance to the sample before. So we recommend always to prepare a number of samples, obviously, and then to test some more, and then this is how you will find out the threshold and the limits of the sample.
And to this question, if Mr. Corey Lamb is asking for testing the same type of sample in 10 different batches with 10 different samples of the same type, and you have 10 results, would you recommend averaging the results?
Yes, they can do this. This is how they can find their threshold, for example. They can do this. Thank you.
Then in that case, if you have more than one test for the same type of sample, then of course you can average and determine the threshold of the sample. Okay, yes, Mr. Corey Lamb explains to me that the question is what I came in the second time, so I think it is answered. And also, I have from Mr. Poutiedat a question: what thickness of film you suggest for the film shrink tester, the FST? Probably he owns an FST, and for C631.
So that's a good question. That actually came up yesterday as well. And so the answer to that question is that it's not really a question of recommending the thickness. You have to take into account, what the machine is designed for. But the thickness is not the issue with the samples. The issue with the samples is what kind of force do they exert. So the limiting factor is not the thickness necessarily, it's the amount of force and the amount of shrinkage which the specimen exhibits. So as long as the forces are within the range of the load cell and the displacement is within the range of measurement of the laser, then the thickness doesn't really matter. But we have to be realistic and take note of what the machine is designed to do. So it's designed to measure thin film. So it would be unusual for somebody to put in there a specimen of, say, 5 millimeters thick or so. But in theory, it's possible to measure specimens that thick. It just depends upon how much force and ratio you're trying to measure.
If I continue the question, is there a maximum and minimum in thickness?
Again, it depends upon what kind of force that the materials measure. So the only way you can provide a definitive answer would be to test those materials which a customer has an interest in testing at the thickness that he's interested in using. So I can't give you a definitive answer on the thickness.
So sorry, just to add on this, thank you everyone. To add on this, so it's not necessarily the thickness, it's about the load cell itself. And I think also this is what Martin is explaining. So if the film, when it shrinks, if it maxes out the load cells, then this is where the limitation stands, not in the thickness of the material. As in the tests that we have performed here in the testing lab that we have in Germany, we have for this specific tester, we have never received or encountered a film that was thicker than 1 millimeter. So this is from our experience from here. Thank you.
The question is raised because I have exactly the following. I have FST02, which gives me varying result with 12 micron film. Can we expect a better result in C631? That's the question.
Possibly it depends upon what the reason behind the variation is. But as I said in the presentation, the goal of the development of the C631H is to reduce the variation which was implied in the system of FST02. So you remember we talked about the LVDT and the friction which that introduces into the measurement. And we talked about the fact that those instruments, the FST02 has a pneumatic sample draw, which with the best will in the world, we couldn't eliminate all the vibration from it. And so it contributes also to the inaccuracy or imprecise nature of the results. So the intention in eliminating the sample draw and eliminating the LVDT is to improve the accuracy and repeatability of the test. So it's not unreasonable to expect a better result, but we would need to try and make a comparison for Mr. Faisal.
Yeah, exactly. What I see here is that since we use a laser displacement sensor, the sensitivity of the testing sensor has been radically increased. So I would expect a higher sensitivity, better accuracy, and of course, less of the varying result. This is what I would expect. The same question about minimum and maximum thickness has been raised by Mr. Naum as well. I think that has been answered, but I keep a reservation to come back with a more detailed answer. And finally, I have one question from Mr. Ihor Polyakov. Can we buy a knife for making samples standard sizes? The cutter for the standard sample sizes comes to the tester set by default, so you don't have to buy it separately. It comes to you with the whole tester. It is exactly. Alex is showing you. Here is the set that you receive, so you have everything in front of you to prepare your samples. And with this, I believe that we conclude our webinar. Looking forward to see you in our future webinars with equally interesting subjects. Labthink has a wide product portfolio. It is specialized to film and flexible package testing, and only to this. But for film and flexible package, we are the one-stop shop. There is a tester you need, name it, and we have it. So thank you very much. Thank you, the Labthink staff, for all the infrastructure and the preparation. And I wish to all of you a nice and productive day. Thank you very much.
Thank you, George. Thank you, everybody. Bye-bye.
Thank you, everyone. Thank you. Bye.
Bye. We will dismiss the meeting.